All right, so today we're going to go a little bit further with vectors and scalars. In our one-dimensional motion unit, we talked a little bit about these two concepts, but we're going to take it even further today. So before we get into too many examples, can you just take a moment and read through these review questions, and then go ahead and hit pause, and then answer these questions, and then when you're ready, hit play, and I'll come back and give you the answers. So go ahead and hit pause, take a look. All right, so number one says, what is a vector? Provide an example of a vector quantity, and then what symbol do we use to represent a vector? Well, a vector is a quantity that has both magnitude and direction. So it's going to have a number with a direction. An example of a vector quantity, in our last unit, we talked about gravity. The force of gravity always acts down. So we'd say the number in that case would be the 9.81 meters per second squared. And then we put the negative in there because that indicates that the acceleration from gravity always goes down. The symbol that we use to represent a vector is an arrow. Number two, what is a scalar? Provide an example of a scalar quantity. So a scalar is nice because that's just a magnitude or just a number. So an example of a scalar that probably gets used all the time would be like your ACT score would just be a scalar. So it's just a number. Your GPA, just a number. Time, it's 2:30 in the afternoon. That's just a scalar. So it just tells you one piece of information with no direction. It wouldn't really make sense if they told you your ACT score and they said like, oh, your ACT score is 34 northwest. So the direction in that case doesn't make any sense, right? Number three, if Mr. L, that's me, walks north of the airport at a velocity of 2 meters per second, and then he steps onto a moving sidewalk also going north at 2 meters per second, what's his resultant velocity? And I call it a moving sidewalk because I asked a person at the airport one time what's the technical term, and the guy said, oh, we just call them moving sidewalks. But if you picture this, it's like the belt of the airport. So there's me, my vector, and it's going north, so I drew it up on my page here. And it says Mr. L is going 2 meters per second. So there's 2 meters per second. And then I'm at the airport, I want to go a little bit quicker. So I go ahead and I step on the moving sidewalk, and it says it's also going north at 2 meters per second. So I was the first vector arrow, and then now here's the second vector arrow. Sorry about the handwriting here. We're doing our best and forgetting the rest. So it says, what's my resultant velocity? Well, these two vectors are lined up with each other, so we can always add vectors. So it's just going to be 2 plus 2. So my resultant vector would be twice the length, and mine's not going to be perfect because I'm running out of space, but it would have a magnitude of 4 meters per second. And then I drew my arrow going up because the direction in this case would be north. So the reason that you get onto those moving sidewalks is because it combines with your velocity to give you a faster resultant velocity. And then it says, what if I started walking south at 2 meters per second? So basically, instead of having this arrow go up at 2 meters per second, if I were to turn around and walk backwards, well, I'm just going to flip this here. So this would be like this. So this arrow would be 2 going that way. Well, in that case, the vectors would cancel out, and I would actually be going 0 meters per second, which is basically how a treadmill works, right? Like you run one direction at 7.5 miles per hour, the belt goes the other way, and then the two velocity vectors cancel each other, and you don't go anywhere. Number 4, if a plane flies east at a velocity of 100 miles per hour and a wind blows west at 20, what's the resultant velocity? Well, north, south, east, west. So in this case, I'm going to say my velocity vector for my plane is going east this way, and that's 100 miles per hour. And that's east right there, miles per hour. I'm not going to put the units on there just because I'm kind of getting squished for room. So in this case, you're going to say, and then the wind's going the opposite at 20, so I'm going to draw it about 1/5 the length, so maybe something like that. It's 20. So you have these two vectors, and in this case, I know it says a plus right there, but you're really subtracting two vectors. So in this case, it's going to be 100 minus 20, means you're going to have a little bit shorter vector over here. So you'll have a resultant vector, velocity vector, of 80 miles per hour, and it would be to the east. Cool. So there's just a little bit of review. If you ever saw this movie, Despicable Me, there's a really good video clip where you have, I think his name's Gru. I saw this movie at one time, but you got Vector over here is his name. So in the movie, he has a pretty good scene where he actually defines what a vector is, and I'll put that link in our lesson plan for today so you can check it out. Thinking physics question. If you flew in an airplane from Minnesota to Florida to see the Minnesota Twins spring training, is it a shorter flight time-wise when you fly from number 1, Minnesota to Florida, 2, Florida to Minnesota, or 3, flight time is always the same? And I'll just point out here, so here we are in Minnesota right here, and we're going to go to Florida, which is down here. Boom, and Mr. K. Laurent and myself would go see the Twins spring training back in the day. So we'd get on the plane, we'd fly down to Florida, down at Fort Myers right here. And the question is, if you started a stopwatch and you were to time it, is it a shorter flight time-wise when you go down to Florida? Or is it a shorter flight time-wise when you come back, Florida to Minnesota? Or is it a trick question? Mr. Lent's trying to trick you and it's always the same. And notice we're not talking about daylight savings time or anything like that. We're just saying is if you started a stopwatch on the plane and you were to measure the time on that stopwatch, which case is it a shorter flight? So think through what you know about vectors so far, or maybe other things, and see if you can reason this one out. And go ahead and hit pause, and once you feel like you have an answer, come on back. All right, so let's take a look at this. This is a weather map, basically, of what's called the jet stream. So this is basically how the air flows across the United States of America. And usually this obviously changes throughout the day, but I just went to the Weather Channel and I grabbed one of these jet stream maps because the general trend is that the weather comes from the west and moves towards the east. And yeah, it obviously changes depending on seasons, but the one thing that doesn't change is it always comes from the left part of the United States, whether it be a little further south or further north, and moves to the right. So if you look at this map, the right answer from back here is it's a shorter flight time-wise when you go from Minnesota to Florida. So I'll circle that one right there. And the reason why is because we were adding vectors. So if we start right here, where the red dot is, and we notice it's kind of a light blue, royal blue color, according to our key, that means that jet stream, that wind is going 80 miles per hour. Well, if the wind up there, when you get up there in the plane, it's going 80 miles per hour, and your plane starts to take off towards Florida, that's a horrible arrow, by the way, I apologize. But if the wind's going 80 and your plane's going 500, well, you can vector addition, add those two together. So your plane's going to have a resultant velocity of 580 miles per hour when it starts off. And you can see as it gets through kind of these mid-Atlantic states, I feel like a weather person all of a sudden, the wind speed picks up even more. So as you fly, you're actually vector addition, you're adding the velocity vectors. So you're going quicker, quicker, quicker. So you're going faster on your way down. And then if you picture it, when you come back, you have to fight the jet stream. So when you fly to Florida, it's faster going and it's slower coming back. And you might think, well, I haven't been to Florida. Well, if you've flown out to California, it's slower going to California because you're fighting the jet stream, and then it's faster coming back. So that's why the times change. It's not just because you're tired on your trip coming back. It seems like it's longer. Sometimes I've had students say that. In your notes, you just want to jot down these 3 terms for vector examples. They're terms that once you actually are familiar with them, you actually hear them all the time. Weather, whether you're going on a plane, tailwind, headwind, crosswind. And I did not decide to draw planes for you today, so you can go ahead and sketch those in your notes, and I won't judge you on your drawings, but you have a plane, and you can see this is called the tailwind. So in this picture, the plane's velocity vector would be here. So here's the plane, is this velocity vector, and then that little red vector represents the wind. So if they say you have a tailwind, that means the wind is coming from the tail of your plane and it's going with you. And then a headwind, you can see you're flying into the wind. And then a crosswind, that wind is at a 90-degree angle. So in your notes, you just want to define what a tailwind is, what a headwind is, and what a crosswind is. And the question is, which plane would be traveling the fastest? So if you're looking at these pictures, you have vector addition going on in the tailwind example. So basically, that's why we fly faster to Florida, because our plane might be going 500 miles per hour and the wind might be going 80. So vector addition means, in that case, you'd be going at 580 miles per hour. So when you have a tailwind, you go quicker. And now let's look at a headwind. So that'd be a 580 miles per hour. And then a headwind would subtract off. So basically, if your plane was going 500 and your wind was going 80, then the resultant velocity for that plane would be 420 miles per hour. And you might not think that makes a big difference, but it actually is a huge swing. So in one case, you're going 580. In the other case, you're going 420 miles per hour. And the last example would be a crosswind. So a crosswind, basically the plane's flying straight and the crosswind is going at a 90-degree angle. So I'm just going to draw in here like this. And in this case, it would actually cause you to fly faster as well. And we're going to talk about that in a little bit. I will put in the lesson plan, it says check out the link in today's lesson plan. I had a student in my class 2 years ago who was getting his pilot's license. And I talked about this, and he totally turned it back around on me and said, Mr. Laurent, well, if you're landing your plane, which one do you think is the most difficult situation to land in? And to be honest, I didn't really know. And so Dalton was very nice, and he explained to me that if you're going to land a plane, the tailwind just makes you go faster. The headwind slows you down. But the crosswind is very challenging because if you picture this, your runway is straight, and the wind is blowing you to the right. So to counteract that crosswind, you actually have to fly into the wind. So this plane would actually have to start to fly this way a little bit to kind of counteract the crosswind. And in the video link that I have today, you'll see planes landing in a crosswind where they've turned into the wind to try to counteract the wind so they can land straight on the runway. And it's pretty scary. So the next time you're on a plane, just pay attention to what the captain's saying as everybody's kind of getting on board. They're going to make one of two announcements. They're going to be like, oh, this is my best impersonation of a pilot, by the way. Ladies and gentlemen, welcome aboard our flight Delta 772 from Minneapolis to Fort Myers, Florida. We do have a pretty solid tailwind today, which means we're going to make some great flight time. So go ahead, sit back, smooth sailing ahead, and enjoy our flight here. Or you might get this announcement. They might be like, ladies and gentlemen, welcome aboard. Sorry for the delay. We are going to be fighting a pretty steady headwind as we make our trip today into San Francisco, California. So flight time is projected to get there on time. But as always, we appreciate your patience as we make our departure onwards to San Francisco, California. Thank you for flying Delta. Have a nice time and make sure you fasten those safety belts.